Hello students, now we are going to uh, discuss voltage divider biasing. Now already I told you in a DC biasing of BJT what are the uh, parameters or what will um, assume so that we will get a amplified output, means for faithful amplification there are already we have already been described three biasing methods like your fixed biasing, collector to base bias, emitter bias. Actually what happened in the previous biasing, so the stability, as far as the stability point of view, we have to judge whether this particular biasing method is suitable or not for transistor biasing, means for to get a good amplification or faithful amplification. So we require a suitable biasing method so that we will achieve a good output. So in previous biasing methods like your fixed biasing or collector to base bias or feedback bias or emitter biasing, what I have seen, and particularly in case of fixed biasing, the stability factor SF equal to 1 plus beta. So there are three transistor parameter, already I told you, three parameters like is your ICO, leakage current, beta and VV. So leakage current already I mentioned, there is a thermal runaway condition may arise due to when the transistor will operate, heat is developed within the transistor. If the heat is developed, for every 10 degree centigrade rise in temperature, the leakage current doubles. So if we will not stabilize the Q point, the transistor may burn because of the cumulative process of heating effect of the transistor will burn. To avoid that, we will choose a suitable biasing method. Another parameter, that is your beta. In beta is a current amplification factor, that is your output current by input current. So in a same manufacturing company, the beta value cannot be controllable in our hand. So one transistor may be 50, another transistor may be 100, another transistor may be 150, 200 like this. So that is inherent variation of the beta value. So we have to stabilize the Q point. So beta value cannot be controllable as far as manufacture of the transistor is concerned. The same beta value we cannot manufacture lakhs of transistors. So that the beta value vary from transistor to transistor. It is one of the transistor parameters. Then another one is your VB, base emitter voltage. In base emitter voltage, VB, what happened? It is your 0.3 volt for germanium transistor and 0.7 volt for silicon transistors. So when the transistor will operate, it is developed within the transistor. For every, the VB value decreases for every 25 millivolt per degree centigrade rise in temperature. When the transistor will operate, temperature will increases. When the temperature will increases, then again what happen? The VB decreases. VB is your cut-in voltage or threshold voltage. If the minimum voltage will not supply or provide to the transistor will not operate. So that to avoid the VB, the decreases value of VB, or to avoid thermal runaway, or to avoid the beta value, it vary from transistor to transistor, we have to choose a proper biasing method or suitable biasing method so that the Q point does not disturb. Q point means the zero signal values of collector current and collector emitter voltage. If we will not choose a proper biasing method, or then what happen? Thermal runaway condition may arises, and also the VB value may be decreases like that. So in previous biasing method, the particular biasing is suitable or not can be judged by a formula. Already I told you a general expression for the stability factor. In general expression for the stability factor, in case of fixed biasing, SF equal to, that is your 1 plus beta. Here, whatever the beta value, it is a constant value, SF equal to 1 plus beta, the beta value, the stability factor is not decreases. If the value of the stability factor is less, the stability is more. So that's why our importance is to how much the minimum value of the stability factor. So minimum value of the stability factor, what happened? So we have to choose a proper biasing method or suitable biasing method. In case of fixed biasing, already I told you in previous lecture, SF equal to 1 plus beta. In case of collector to base bias or feedback bias, the stability factor SF equal to, that is your 1 plus beta divided by 1 plus beta, that is your RC by RB plus RC, RC by RB plus RC. Here RC is your feedback resistor. Here this value, it is provided the stability. The value of RB is much greater than RC as per design point of view. If this value of this factor is more, that means overall this value of the stability factor will be less. it is somewhat better than your fixed biasing. Then already another biasing already I told you in a previous class, SF, that is your emitter bias, SF equal to that is your 1 plus beta divided by 1 plus beta, that is your RE by RB plus RE. This is your what? This is your for your emitter biasing method. In case of emitter bias, the value of the stability factor is like this. That is your here this RE by RB plus RE. This RE provided the stabilization as far as, and this biasing is better than your fixed biasing and your collector to base bias. Already I told you these three biasing schemes. Already I told you in your previous lecture. So now today we will discuss that is your voltage divider biasing. In case of voltage divider biasing, what happened? It has two approach, or it has two approach. That is, one is your approximate analysis, another one is your exact analysis. What is approximate analysis and what is exact analysis? In case of approximate analysis, what happened? So in case of voltage divider biasing, here in this is your voltage divider biasing circuit, and if you observe, there is a capacitor here, that is an input capacitor, and this is your coupling capacitor, and this is your emitter bypass capacitor. So in case of, as now we are going to calculate the DC current and DC voltage. In DC, this capacitor will be open circuited because the reactance will be more, and the reactance will be more, that is, this can be open circuited. All the capacitors can be open circuited in case of what? That is your as far as we are going to calculate the DC current and DC voltage. In case of approximate analysis, so we can just remove the capacitor. Now we are going to calculate what? The DC current and DC voltage. That's why the capacitor can be open circuited. The capacitor can be open circuited here. So how to calculate the DC current and DC voltage in case of approximate analysis? In case of approximate analysis, so there is a condition. So what is the condition? In approximate analysis, there is condition is what? That is your beta RE must be greater than equal to 10 times R2. This is a condition. Beta RE, as far as the design point of view, so beta RE greater than equal to 10 times R2. If voltage divider biasing is given, if this condition is satisfied, the value of beta is given, it may be 50, it may be 80, maybe 100, whatever value of beta, multiplying with the emitter resistor, it's the value of beta RE must be greater than equal to 10 times R2. If this condition is satisfied, then we can proceed approximate analysis to get DC current and DC voltage. In beta RE greater than equal to 10 times R2. So in case of approximate analysis here, what happened here? This is this value, this R1 and this is your R2. First of all, this value, this voltage is nothing but your V2, say, and this voltage is nothing but V1. So VCC equal to this voltage plus this voltage is nothing but that is your VCC supply voltage, that is your collector supply voltage VCC. So VCC equal to, or we can calculate this value V2. Since R1, R2, in case of approximate analysis, we have neglected the base current here. This current equal to, in this current equal to this current plus this current. This is your, this current, let this is your I1, this current is your let I1, and this current is nothing but I2, and this current is nothing but IB. In the approximate analysis, we have neglected the base current IB, so that I1 equal to I2 and the R1, R2 become series, and the total voltage is nothing but VCC. Then we are going to calculate the value of V2. So V2 value is how much? V1, this voltage across R1 is your V1, voltage across R2 is your V2. So V1 plus V2 is nothing but what? That is your VCC. So that's why, first of all, we have to calculate the value of V2. The V2 is how much? V2 equal to, that is your what? VCC into R2 by R1 plus R2. VCC into R2 divided by R1 plus R2. How? Because the current in resistance with I2 into R2. So V2 is nothing but what? V2 equal to I2 into R2. I2 into R2. Since I1 equal to I2 equal to I, the current I1 equal to I2 equal to I, because the series current is same. The value, what is the value of I? The value of I is how much? The value of I equal to how much? That is your total voltage. Total voltage is VCC. VCC divided by what? R1 plus R2. Okay. So if I equal VCC by R1 plus R2, V2 is nothing but what? I2 into R2. So V2, it is nothing but what? I2 into R2. So I2 into R2 is nothing but V2. That's why I2 equal VCC by R1 plus R2 into R2. So V2 value is nothing but VCC into R2 divided by R1 plus R2. Then applying Kirchhoff's voltage law to the base emitter loop. This is your base, and this is your base, this is your collector, and this is your what? Emitter. Then we will apply the Kirchhoff's voltage law to the base emitter loop. Apply KVL. Apply Kirchhoff's voltage law to the base emitter loop. If we apply KVL to the base emitter loop, what is my equation? So minus to plus is plus, plus to minus is minus. If there is a resistor, multiplied with current. If there is a voltage, and written as it is. So this is your V2, minus to plus is your plus. So this is your V2, this is your V2. Then here there is a plus to minus minus. If there is a base and this is your emitter, there is a potential base at base emitter is nothing but is a VBE. We should consider the base emitter voltage, that is a VBE. V2 minus VBE. Then the current is flowing like this. This is your plus and this is your minus. So this is nothing but what? Current. Since this is your emitter terminal, current flowing this resistor is nothing but emitter current. Since it is a collector, current flowing this is nothing but collector current. So that's why this is your RC. So VB and plus to minus minus IE RE equal to 0. This is my equation. If you apply KVL to the base emitter loop, that is your V2 plus to minus minus, there is a voltage between base and emitter, there is a voltage VBE. Already you should consider. If you move from base to emitter, there is a voltage, that is a VBE. The V2 minus VBE minus IE equal to 0, or V2 equal to VBE plus IE. So this is my one of the input equation in case of if you consider the approximate analysis. So that is this is my input equation. First of all, you will calculate the V2. Then after calculating V2, then apply KVL to the base emitter loop. You will get this equation. From this equation, you directly find out the value of IE. So what is the value of IE? Or IE equal to the value of IE equal to how much? V2 minus VB and divided by what? That is your RE. So in this way, you can calculate the DC current and DC voltage. Similarly, if you apply KVL to the output loop, what is my output equation? If you apply KVL to the output loop, as far as your understanding, now I am forming a loop. This is a loop, closed loop. This is VCC. From this to this is nothing but your VCC. That's why this is nothing but what? That is your VCC. If I will apply KVL to the output, apply Kirchhoff's voltage law, apply KVL to the output loop. What is my output equation? Here the current flowing is like this, plus to minus here. Here minus to plus plus, that is your VCC. Again what? Again this is your entering end and this is your leaving end, and obviously the current flowing through the RC is nothing but IC, collector current. So that is your IC into RC, plus to minus minus. So minus IC RC. Then always you consider if there is a transistor is a 3-terminal device. So in between base and emitter there is a voltage VB. In between collector and emitter there is a potential, that is your VCE. So VCE, one of the point of the operating point, that is your collector to emitter voltage. So if you move from this to this, that is your what? So this is plus and this is minus. You should consider this is nothing but what? That is your collector emitter voltage VCE. If you apply KVL to the output, what is your output equation? VCC plus minus minus ICRC plus minus minus VCE. Then plus minus minus IE RE equal to 0. First of all, if you apply the proper Kirchhoff's voltage law to the input and output, you will get the two equations, input equation and output equation. Using this input equation and output equation, you can calculate the DC current and DC voltage. If you apply KVL to the output, and this is your output equation, VCC minus ICRC here plus to minus minus VCC, here plus to minus minus IC into RC, here plus to minus minus, that is a VC, here plus to minus minus IRE equal to 0. This is your output equation. So using equation 1 and 2, you can calculate IB, IC, VC, V, VB, all these DC current and DC voltages. It is all about your approximate analysis as far as voltage divider biasing is concerned. In case of voltage divider biasing, we have neglected this current IV, so that I1 equal to I2 equal to I, you can directly apply Kirchhoff's voltage law to the base emitter loop. If you apply KVL to the base emitter loop, V2 minus VB minus IRE, from this equation you will calculate value of I also here. Okay, so in this way we have analyzed the voltage divider biasing using approximate analysis, but the condition is what? The condition is beta RE must be greater than equal to 10 times R2. Beta value is given, RE value is given, R1 value is given, and R2 value is given. First of all, you have to check if beta RE greater than equal to 10 times R2, you can proceed to calculate the DC current and DC voltage using approximate analysis. So next, exact analysis. Exact analysis. Exact analysis. In case of voltage divider biasing, here as already I told you, the capacitor is open circuited because in a DC the capacitor there is a infinite reactance, it can be open circuited. So this is your voltage divider bias circuit, this is your R1 and this is your R2, this is your RC and this is your RE. So now for easy understanding, I have split this circuit so that you can easily understand. So how we will proceed to calculate the DC current and DC voltage if the condition is not met, that is your approximate analysis beta RE greater than equal to 10 times R2. For exact analysis, so I can split this circuit into in this way. So like this one. So here this is nothing but VCC. Same VCC is supplied both input and output. Same VCC is supplied both input and output. Okay. So here, first of all, in case of exact analysis, that is input, that means, so here we have to, the input circuit can be modified a Thevenin's equivalent circuit. In case of voltage divider biasing, in exact analysis, here in approximate analysis, this is your I1 and this is your I2 and this is your what? IB, here this is your IB. In exact analysis, we cannot neglect the base current IB, so that the equivalent Thevenin's equivalent circuit we have to put in case of voltage divider biasing. What is my input voltage here? What is my equivalent resistance? That is your, here if you look here, like that is your VTH and RTH, Thevenin's voltage and Thevenin's resistance. The input here, the input can be open circuited here. The input can be here, the input can be open circuited, and you have to find out the Thevenin's voltage and Thevenin's resistance. So Thevenin's voltage, to find VTH, to find Thevenin's voltage, to find Thevenin's voltage, Thevenin's voltage, Thevenin's voltage, VTH. Okay. So in case of voltage divider biasing, the input circuit can be modified a Thevenin's equivalent circuit. In Thevenin's equivalent circuit, how to calculate VTH? So here, that is open circuit voltage, voltage across R2. The voltage across R2, VTH equal to VCC into R2 divided by R1 plus R2. So like what? So I am going to calculate here, that is your VTH and RTH. So VTH equal this voltage. That means this is nothing but what? A closed loop. So this is your I2 into R2, I into R2. What is value of I? I value is nothing but VCC by R1 plus R2. Already I told you. So this is your I into R2, VCC by R1 plus R2, that is your I current, and R2 nothing but voltage. So I into R2 is nothing but VTH. VTH or V open circuit voltage VTH equal VCC into R2 by R1 plus R2. Then Thevenin's resistance. Thevenin's resistance. Thevenin's resistance. Thevenin's resistance is nothing but RTH. How to calculate Thevenin's resistance? VTH, RTH, like what? So this is nothing but your, to calculate the Thevenin's resistance, all the voltage source should be short circuited and current source open circuited here. And let this is your R1 here, and this is nothing but what? R2. And here VCC, this voltage VCC is applied from here. This is nothing but VCC. This voltage source should be short circuited here. If the voltage source should be short circuited like this, now if you look here, that is your what? What is my RTH? What is my RTH here? What is RTH? This R1 is comes parallel to R2. In Thevenin's resistance RTH, so RTH is nothing but what? RTH equal to R1 parallel to what? R2. If the two resistance are parallel, equivalent resistance is nothing but what? Product of the resistance by sum of the resistance. So RTH value, RTH is nothing but R1 parallel to R2. Okay. So already I told you what is VTH and what is RTH. So the input circuit, the input of the voltage divided by circuit can be modified by Thevenin's circuit. So what? The resulting circuit is like this. The input circuit of the voltage divider bias can be modified into Thevenin's equivalent circuit. One is your VTH, another one is your what? That is your RTH. And here this is nothing but what? Whatever the output as remains same, and this is nothing but what? Plus VCC. Here this is nothing but RC, and this is nothing but your RE here. The circuit is modified into like this. The input can be modified into what? Thevenin's voltage and Thevenin's resistance. So Thevenin's voltage is nothing but what? VCC into R2 by R1 plus R2, and Thevenin's resistance is nothing but R1 parallel R2, that is your R1 R2 by R1 plus R2. So input of the voltage divided by circuit can be modified by Thevenin's equivalent circuit like VTH and RTH. Then we will apply the Kirchhoff's voltage law to input and output. So apply KVL to the input. Apply Kirchhoff's voltage law to the input loop. To the input loop. Apply Kirchhoff's voltage law to the input loop. If I will apply KVL to the input loop, already I told you, if there is a base, this is your base, this is your base, and this is your emitter, and this is your what? That is your collector. In between base and emitter there is a potential. So already you have to consider VB between base and emitter. Similarly, already I told you between collector and emitter there is a potential. You have to consider, that is your what? VCE. You should not neglect VB and VCE. When you are going to apply KVL to the input and output, you must consider base emitter voltage VB, and you must consider the collector emitter voltage, that is your VC. If you apply KVL to the input, what is my input equation? So here minus to plus plus, that is your VTH. Here there is a current entering, current, if current flowing is like this clockwise, so that's a plus to minus minus. The current flow through the RTH is what? That is your base current. Since it is connected to the base, the current is base current IV. In previous approximate analysis we have neglected the base current because I1 equal to I2 equal to I. Here in case of exact analysis we have to consider the base current. We can neglect the base current. So here if we apply KVL to the input, what is my input equation? VTH plus minus minus base current, that is your IB into RTH. Here base current IB into RTH. Here plus minus minus, that is your VB E. Then plus to minus here, plus minus minus, current is flowing through the emitter terminal is nothing but emitter current, that is your I into RE. minus IE into RE equal to 0. So this is my input equation, or this is your equation number 1. Slightly modified the modified the emitter current. Emitter current already I told you, emitter current is nothing but base current plus collector current. So in place of emitter current, so VTH minus IB RTH minus VBE minus, in place of IE you can write that is your IB plus what? IC into RE equal to 0, or VTH minus here the term containing IB, here also the term containing IB. So here minus, if IB taking common, that is your what? RTH, and minus this here minus IB RE plus RE. Then minus VBE minus IC RE. Okay. This is your equation number 2. Okay. Next, we will apply KVL to the output. When we will apply the Kirchhoff's voltage law to the output, apply KVL, Kirchhoff's voltage law to the output. What is my output equation? Here VCC, the loop is like this. Okay. Here this VCC, that means what? This to this is nothing but VCC. That's why this is nothing but VCC. So the loop is forming like this. So plus VCC, here the current entering is plus, leaving minus, plus to minus minus. Current is flowing through the collector terminal. This is your collector current, IC into RC, plus to minus minus, that is your VC, plus to minus minus, emitter current into RE equal to 0. So my equation is what? VCC, here plus to minus minus, ICRC, plus to minus minus, VCE, plus to minus minus, IERE equal to 0. This is my output equation. Or VCE equal to how much? VCE equal to VCC minus ICRC minus IERE minus IERE. So this is my output equation. Using this equation 1 and 2, you can calculate the DC current and DC voltage. Now the important point is to analyze the whether this biasing scheme is suitable or not by means of stability factor. In stability factor, already I told you the general expression for the stability factor as far as stability point of view, the particular biasing is suitable or not by means of stability factor. In case of stability factor, there is a general expression, already I told you, the SF equal to 1 plus beta divided by 1 minus beta DIB by DIC. So this is your general expression for the stability factor to judge a particular biasing scheme is suitable or not by means of the stability factor. If the value of the stability factor is less, the stability is more, and vice versa. If the value of the stability factor is more, the stability is less. We should avoid this biasing scheme, and to get we have to avoid the biasing scheme if we will not properly selected a particular value of IC and VC. If the stability factor means what? The operating point IC and VC, it should be independent of the variation of the transistor. In particular, this voltage divider biasing scheme, to analyze the voltage divider biasing scheme is suitable or not for transistor biasing by using this stability factor expression, SF equal to 1 plus beta by 1 minus beta DIB by DIC. Beta is a constant and this is a DIB by DIC. So differentiating base current with respect to collector current. Using this equation 1 here, equation equation 2, the value of IB is what? IB equal to this expression minus of IB into RTH plus RE. If it is to the right hand side, it becomes plus. So IB value is how much? VTH minus VB minus IRE divided by what? RTH plus RE. This is the value of IB. Actually, this value of IB means what? For the particularly to judge the stability factor, stability point of view, we are using this expression IB equal to VTH minus BB minus RE by RTH plus RE. If we are differentiating this expression with respect to IC, differentiating with respect to IC, what is my DIB by DIC? DIB by DIC is what? Remember, VTH. The value of VTH is how much? VTH is what? VCC into R2 by R1 plus R2. VCC is a constant, maybe 10, maybe 20, whatever the value of VCC is a constant. R1, R2 is a constant because R1 is maybe 50 kilo ohm, it may be 100 kilo ohm like this, and it is also a constant. The value of the total value is also a constant. If you differentiate in the constant, the value will be 0. So that's why what? So the VTH is a constant, differentiation of this constant will be 0. VB is also constant because 0.3 for germanium and 0.7 for silicon. So that's why it is also constant. This VTH is a constant, VB is a constant, and another thing is minus IRE here, minus IRE. So DIB by DIC, what happened here? Because we have not converted IB plus IC here, because differentiating base current with respect to collector current. In place of IRE, in place of I, we can put what? IB plus IC here. So that's why here in place of IE, that is your what? IB plus IC into RE. Why I am putting I in place of IB plus IC in place of IE? Because we have to differentiating IB with respect to IC. That means the term must contain IC. So that's why in place of IE, I can put what? IB plus IC. IB plus IC, this expression. So IB plus IC minus IB RE minus IC RE. If you are differentiating DIB by DIC, because what? The value will be how much? Minus IC RE, because that is your what? IB equal to, that is your what? Minus IC RE by what? RTH plus RE. So all are constant, VTH, VB, all are constant. That's the only thing is IB equal to here, IB equal to minus ICRE by RTH plus RE. If you are differentiating this respect to IC, mean here IC, what is my DIB by DIC? The value will be how much? Minus RE by RTH plus RE. So DIB by DIC equal to minus RE divided by RTH plus RE. This is my DIB by DIC. If I am substituting this value in this stability factor expression, what is my stability factor expression? SF equal to how much? So SF equal to 1 plus beta divided by 1 minus, this is your minus plus, that is your 1 plus beta, that is your RE by RTH plus RE. After getting this one, we have to analyze whether my stability factor is improved or not. Already I told you this RE provided the stabilization here. Here RTH is nothing but R1 parallel R2. So R1 parallel R2 means R1 R2 by R1 plus R2. Remember, as far as the design point of view, this is nothing, that is your R1 and R2. As far as that is your this R1 and this is R2, the value of R1 and value of R2, if high value, one is your low value. So high value parallel low value is nearly equal to your low value. So in case of that is your here, that is your RTH plus RE, this RE value is much greater than RTH. That's why this factor, this RE by RTH plus RE provided the stabilization. So overall the value of the stability factor will be less. If the stability factor is less, the stability is more. So we have to prefer the voltage divider biasing compared to that is your what? That is fixed biasing, collector to base bias and emitter biasing. As far as the design point of view, so we have to choose the voltage divider bias rather than your fixed bias and emitter bias. So thank you. So next class we will study more and more number of problems related to the DC biasing of BJT, like your fixed bias, collector to base bias, emitter bias and voltage divider bias. So how to calculate the DC current and DC voltages, if different types of problems have given, so how will you find out the DC current and DC voltage. So thank you.